answer the question, but I will tell you about some geometries. One geometry that.
Radhika ji, please wait. Please wait.
Oh, you said wait. I thought you said speak. My bad.
Ma'am, now you can start, please.
Now I can start?
Okay.
Yes.
Recording in progress.
Please wait. Please wait, man. Okay, respected head of the department. Can I start? Jigar? Yeah. So, respected head of the department, Professor Neetaben Shah, respected speaker, Dr. Radhika Gupta, Professor Kaushik Thakur, and dear students. On behalf of the Department of Mathematics, I, Dr. Narendra Srimali, welcome you in this talk. Today is International Pi Day, and it is also a birthday of a scientist, great scientist, Einstein. Okay. Dr. Radhika is the speaker of this talk. Dr. Radhika is a research assistant professor at Temple University. She received PhD from the University of Utah. Before that, she completed undergraduate studies from IIT Bombay in engineering physics. Her research is in geometric group theory, in particular, automorphism of free groups, mapping class groups, cat-zero groups, and cube complexes. Her title of the talk is "What is the Geometry of Universe?" So I request Dr. Radhika Gupta for delivering her talk.
Thank you so much for the introduction. Thank you for inviting me. Okay, so in this talk, I want to tell you about one of my favorite geometries called hyperbolic geometry. And we'll see what are the possibilities for the universe to have its geometry to be. So maybe let's first start with what is a geometry. So I think when I say the word geometry, some things flash in everyone's mind, like angles, lines, shapes. We all think about these things from what we learned in high school. And so for me also, geometry of a space will be concerned with properties like finding distance in the space, shapes, size, relative positions, etc. So that's what a geometry will be for us, being able to define certain notions like this. So we are all familiar with geometry in the plane, or R2, as I call, I will call the plane R2, like real numbers cross real numbers. So real numbers cross real numbers. In this space, we have very good intuition for how anything happens. We know if I give you 2 points, P and Q, we know exactly how to find distance between those 2 points. We have a formula for that. That distance, or we can even find the shortest path between 2 points. That's the straight line between those 2 points. So we have very strong intuition for what that means to find the shortest path between 2 points. So this will show up again. It will be important, shortest path between 2 points. In this space, R2, or I guess I'm also using the symbol E2 to mean Euclidean space. We also know how to find angles between two straight lines. We know the sum of angles in a triangle is equal to pi. And the Euclidean 2 space, there is some notion of curvature, which just intuitively, we know that Euclidean space is flat. We know its curvature is 0. It's not bending weirdly. It's the Euclidean space is flat. Now, all the theorems in Euclidean geometry, so the geometry we learn in school is called Euclidean geometry because it's derived from a set of rules which Euclid laid down many, many years ago. Of his 5 rules, there is one which is particularly important, which is called Euclid's 5th postulate. So let me tell you what is Euclid's 5th postulate. So this says in a plane, so in R2, if you're given a line and a point, not on the, I have a picture, yes. So you're given a line L and a point P, which is not on the line. This postulate or this axiom, so Euclidean geometry is based on a set of axioms, and this is one of those axioms. This axiom says there is exactly one line parallel to the given line L passing through P. So when I say two lines are parallel, I mean they don't intersect. So we all have a very good intuition for what this is saying. There is exactly one line passing through P, which is parallel to L. And that's why all these fifth axioms, they are called Euclidean spaces. And I'm highlighting the fifth postulate. And now here's a question for you. Can you think of a space where, Euclid's fifth postulate might not be true? That if I draw, so here is fifth postulate for you again. If I have a straight line, and if I have a point not on the line, then there is exactly one line passing through that point, which is parallel to the given line. Maybe you have seen the space, maybe you haven't. And I guess okay. And a hint is like, this is even a two-dimensional space. So maybe just think, what are the other two-dimensional spaces you're familiar with? You're all familiar with the plane. Which other two-dimensional space comes to your mind first?
Three-dimensional space.
Three-dimensional space?
It should be not true for three-dimensional space.
So it is true, Euclid's fifth postulate is true for three-dimensional space? Because even in R3...
Ma'am, if we take a plane parallel to a line, okay. Suppose we have a line or a segment, as you say, and we take a plane parallel to that line. Plane.
Yes.
Then that plane can have many of lines in it.
Oh, yes. Thank you. That's a great example. I was thinking something else. That's great. But that's thank you. That's a three-dimensional example. Can you think of a two-dimensional one? Okay, so this was a great example. So let me talk about the sphere, and then let's see what happens to Euclid's fifth postulate in the two sphere. So I've colored this, but I'm only thinking about the surface of the sphere. I'm only thinking it's not a solid sphere; it's just the surface of the sphere. So that's why I have a 2 here. So I'm thinking of the 2 sphere. So it's like the surface of Earth. So let's just first talk about its geometry, and then we'll see if Euclid's fifth postulate holds here or not. So in the 2 sphere, the 2 sphere has its own geometry. And how do we measure the distance between 2 points, or what's the shortest path between 2 points? The shortest path between 2 points, I've drawn 2 points X and Y here. The shortest path is defined to be this great circle, the arc of the great circle, not the whole great circle, but this arc of the great circle. So the geometry of the 2 sphere is such that the shortest path between 2 points is arc of a great circle containing those 2 points. And these shortest paths, we call them straight lines, because that's how we think in Euclidean space. So on a sphere, quote unquote, straight lines are not straight. Straight lines are curved. So where I'm using the word straight line to mean shortest path. So these shortest paths are actually curved now. So basically, if I want to go from North Pole to South Pole, I have these longitudes. Yes, longitudes. I have lots of longitudes on which I can walk. And those are all straight lines in spherical geometry. So here is a question for you, which you can think about later. Or if you get bored in the talk, you can think about this. If I give you any 2 points on the sphere, any 2 random points, is there always a great circle passing through those 2 points? So a great circle for me is it's basically an equator. So if I give you in my picture, I've drawn 2 good, like, I've drawn 2 points that are easy to visualize. That of course there is that equator. There's a great circle passing those 2 points. But if I give you 2 points here, X and Y, is there still a great circle passing through any 2 points? So you can think about this later. The answer is yes, but it's a matter of convincing yourself like why. So basically I'm saying any 2 points can be joined by any 2 points on the 2 sphere can be joined by a shortest path. Since we're talking about the spherical geometry or geometry on the sphere, I should say how we measure angles. Angles come from this space sitting inside R3. So if I want let's say I have this point, I have these 2 lines, the 2 great circles that I've drawn. And if I want to measure the angle between these 2 lines, I have these 2 vectors in R3. If I'm sitting in R3, I have these 2 vectors. And I know how to measure angles in R3. So I can use that to measure angles on the 2 sphere. So here is how the spherical geometry starts differing from Euclidean geometry. Now I can talk about triangles. So a triangle for me is basically the 3 sides of the triangle are straight lines or straight segments. So I've taken 3 lines and then I've taken segments from those lines to draw my triangle. That's a spherical triangle and it's fat, it's bulging out. And it turns out that the sum of angles in a triangle in spherical geometry is bigger than pi. And these triangles are, like I said, these triangles are fat. And again, whatever idea of curvature we have in our minds, this space will have positive curvature because it's bulging out. Now let's talk about parallel lines. So I said 2 lines are parallel if they don't intersect. And in spherical geometry, any 2 straight lines always intersect because a straight line is a great circle and any 2 great circles will intersect. So any 2 straight lines always intersect. So Euclid's 5th postulate is kind of not true for trivial reasons because you don't have parallel lines. So if I give you, let's say, if I give you a point and if I give you a straight line, L, any straight line passing through N will have to cross just because there are no parallel lines in spherical. So Euclid's 5th postulate is not true for stupid, like silly reasons, just because there are no parallel lines. And we can understand, I guess my last bullet point here is basically saying the 2 sphere sits inside R3. And that gives us a way of understanding the 2 sphere using our intuition for Euclidean geometry as well. It's very different. Like if a person lives on the 2 sphere, it's very different for them than if they were living in 3 space. It's like us living on Earth. Now that we know Earth is not flat, we know it's spherical. That's very different than if we were living in flat space. But we can still use the ambient flat space R3 to understand the geometry of the 2 sphere. So why am I talking about Euclid's 5th postulate? Because for a lot of time in history, people were trying to show that the fifth postulate is actually redundant. They wanted to say that Euclid's other postulates would give you the fifth postulate. You don't need the fifth axiom. You don't need to assume the fifth axiom. People were trying to prove that the first four axioms were enough to give you the fifth axiom. So people tried very hard to prove this, but they failed for a good reason, because that's not true. So in the late 1820s, these three mathematicians, Bolyai, Gauss, and Lobachevsky, they realized there are geometries that do not satisfy the parallel axiom. So all this time when people were trying to prove that the fifth one is, you can get the fifth one from the other four, they were failing to do this for good reason, because there are geometries where this thing need not be true. So basically non-Euclidean, these three mathematicians, they proved that non-Euclidean geometry exists. And non-Euclidean not in the spherical sense, because that was in some sense a redundant case, but in a stronger sense. And I should say, like the R3 example that somebody gave a while ago. So for R3, so when I'm talking about lines and points, when I go in higher dimension, I would have to talk about planes and points, and then I would have to talk about higher dimensional lines. That's how I would talk about Euclidean geometry in higher dimensions. I'm talking about lines because I'm only talking about 2 dimensions. So like R3 is still Euclidean. It's not non-Euclidean. Even though the lines example was correct, but it's still Euclidean. Because for R3, my fifth postulate would be for planes and not lines. Okay, so these people established that non-Euclidean geometry exists. So let's try to understand this space that they came up with. And what does the space look like? So this geometry that these mathematicians came up with, that's called hyperbolic geometry. And in order to understand this space, Beltrami constructed some models of hyperbolic space. So that's what I'm going to explain now. So when I say a model of hyperbolic space, it's like a map of hyperbolic space in Euclidean space. So my eye can only see Euclidean space. We are so used to Euclidean stuff around us. Our eyes cannot see hyperbolic directly in some sense. So I want to make these maps from hyperbolic space to Euclidean space so that I can try to understand what's going on. So this is like saying, so we know like Earth is spherical, Earth is not flat, but we can still make, in geography classes, we still draw maps of Earth and maps of the world, and they are like flat maps. And using those flat maps, we still get some intuition for and some understanding for what's going on the spherical Earth. So similarly, I want to explain some maps of hyperbolic space. So for when we study like maps of Earth on R2 or on the plane, you might have heard of the word stereographic projection. So I won't be doing stereographic projection, but just giving you a sense for what I'm going to do next. I'm going to explain some models or some maps of hyperbolic space, of hyperbolic 2 space for this talk. You can define hyperbolic space in any dimension, but for this talk, we're just going to do in 2 dimensions. We're going to build these maps in Euclidean space. Any questions so far? Okay. So I'll show you 2 models. So the first model is called the hyperboloid. It's called the hyperboloid model. And you can take this to be the definition of the space. Okay, so we have R3 our Euclidean 3 space. And usually we have a notion of dot product on the space, right? If I give you two vectors and if I ask you for its dot product, we know how to find that dot product. And in fact, that dot product can basically gives us a lot of information. Like the usual dot product gives me the length of a vector. So it's just like x square plus y square plus z square, like square root. It also gives me the angle between two vectors because I know cosine theta is equal to, and I can write a formula in terms of dot products. So it gives me lengths, it gives me angles and like more things. So dot product really captures a lot of geometry of the space. And this is our usual dot product. And now I want to define a new dot product. So this new dot product is the star. And that new product is basically xx prime plus yy prime minus zz prime. So I've changed that plus to that minus. So R3, just that space, that topological space with this new dot product, that's called Minkowski space. And this shows up in physics a lot. But for us, I'm just thinking it's R3 with this new inner product. And in this new inner product, now I want to look at this equation and the locus of this equation, x squared plus y squared minus z squared equals to 0. So I want to see in R3, what does this look like? And I want to see what does x squared plus y squared minus z squared equals to minus 1. What does that look like? So I've drawn a picture. So for the first one, x squared plus y squared minus z squared, I get this cone picture. That's the locus of the first equation. And the second equation, I get this, I guess I get these two sheets, and these are called hyperboloids. Perhaps I should have drawn all this in like one dimension lower, and then we would actually get our hyperbola. Like imagine there is no y, then I would be getting hyperbolas. Maybe I can do this quickly on the side. So if I have just like x squared minus z squared is 0, and x squared minus z squared is minus 1, then if I have the xz plane, and so these are my hyperbola. So I'm just doing it in one dimension up because I want to talk about hyperbolic 2 space. And so like, one of these hyperboloids, that's my hyperbolic 2 space. And the point here is I'm drawing all this in Minkowski space. So I'm not drawing hyperbolic space in usual R3. I'm drawing it in R3 with this funky inner product on it. So the geometry on this hyperboloid is not the Euclidean geometry. It's coming from this inner product, from this funny inner product. So if I'm to like measure angles, the angles will be measured with respect to this inner product and not the usual one. So things can be very different. And that's the goal. We want to understand what are things like. Any questions?
What are application?
Can you say that again?
What are application for this geometry? or
What are the
space?
applications?
Yes, yes.
I'll try to answer that in some time, if that's okay.
Okay, okay.
Yeah. So we're still trying to understand. So I guess I've defined a hyperbolic two space for you, but I haven't convinced you that it does not satisfy Euclid's fifth postulate. Because we are trying to find a space which does not satisfy Euclid's fifth postulate. And in order to do that, I actually want to talk about a different model. Okay, sorry, I have one more slide, which I think I already talked about. How do I measure distances, angles in hyperbolic space? I said it has to be done via this new inner product. And right. And I was trying to say that this hyperboloid that I constructed, it's sitting in Minkowski space, and it actually does not sit isometrically. So isometrically means the way I measure angles. So like when we draw the sphere on the map, when we draw the map of the world on a piece of paper, that's not an isometric embedding because the distances have been distorted. When you put the map of Earth on a flat thing, distances have been distorted. So that's not isometric. And I'm saying that this hyperbolic space is also, if I try to draw it in E3 in Euclidean space, it will be distorted. I cannot put it in Euclidean 3 space nicely. And in the above picture, but in general, Hilbert showed that you can never put it in Euclidean 3 space without distorting things. So basically, this is saying that hyperbolic 2 space is intrinsically very different. It's not as if you can, like the 2 sphere was, I can still put it in R3 and I can still get a grasp on the 2 sphere. But for hyperbolic space, Hilbert showed that you can never put it in R3 without distorting things badly. Okay. So then, so the next thing is I want to talk about a different map or a different model of hyperbolic 2 space called the Poincaré model. So what Poincaré does is he maps hyperbolic 2 space, which we are thinking of as this hyperboloid. He maps this into an open disk in Euclidean space. So this is just people trying to get a better, it's like you have hyperbolic space in your hand and you are like rotating it and you want to like see underneath it, you want to look at it from the side, you want to look at it from the top. And while you're doing all this business, to do all this business, you like, you go from the hyperboloid model to the Poincaré model. So instead of thinking of this as this hyperboloid, you map it onto a disk, just trying to get a different perspective on hyperbolic space. So now when I'm mapping, so I've shown a picture here. So this unit disk is this unit disk. And I've tiled it by triangles just to show you how distorted the picture is. So in hyperbolic geometry, if I was doing like hyperbolic angles and hyperbolic distances, all these triangles will have same size. All these triangles have the same size in hyperbolic geometry. So if I had a hyperbolic ant, if there was an ant which like actually lived in hyperbolic space, it would see that all these triangles have the same size. But to me, with my Euclidean eye, these triangles obviously appear to be getting smaller and smaller. But to a hyperbolic ant, these triangles have all the same size. And that's what I meant that like when I'm trying to visualize hyperbolic space in the plane, it's become distorted. So let's look at this picture again. So like I said, each triangle for a hyperbolic ant, each triangle is the same size, even though to us it looks like they're getting smaller and smaller. So in particular, what that means is if I have to, what are the shortest paths between 2 points in this space? So in this space, if I have 2 points P and Q, the shortest path is actually this thing. And this thing is part of, a circle in Euclidean space, which meets the boundary circle at 90 degrees. So remember, this is all I've projected my hyperbolic space into Euclidean space. So I can talk about these angles being 90 degrees to the boundary. So shortest paths are basically these circles which are intersecting the boundary at 90 degrees. So between any 2 points, I can always find one. Now, because each of these triangles, so now each of these triangles has the same size. So if I walk along this orange geodesic, I'm seeing these triangles which all have the same size, which means in hyperbolic geometry, it should take me infinite time to reach the boundary. So even though like in the Euclidean sense, I'm like, oh, this is just distance 1, because I was mapping it to a disk of radius 1. In Euclidean sense, this is just a disk of radius 1, but in hyperbolic geometry, it'll actually take me infinite time to reach the boundary because each of these triangles has the same size in the hyperbolic world. So this circle, that's called circle at infinity in hyperbolic geometry. And you can imagine, like I took this, like the hyperbolide looks more infinite. I took that and I like squished it onto this disk. So this boundary is actually not there because I've squished this space onto here. Another curious thing about hyperbolic geometry is that sum of angles in a triangle is actually less than pi. So somehow these triangles are thin. So Euclidean triangles look like this. Spherical triangles look fat, and hyperbolic triangles look thin. So I guess we have basically said all these things. Just again, one thing I want to highlight is that every arc orthogonal to the boundary of that disk is a hyperbolic straight line. Because we are trying to understand Euclid's fifth postulate. So let's just remember what are hyperbolic straight lines. So hyperbolic straight lines are these. Oops. Okay, Okay, hyperbolic straight lines are these arcs. Okay. So now we can see why Euclid's fifth postulate fails in this geometry. So I described the geometry by telling you what are the straight lines, what are the angles, and so on. So let's now see. So Euclid's fifth postulate said, if you have a line and a point P, there is exactly one line parallel to L, which is true in Euclidean space. But now I can draw lots of lines parallel to L. So I can draw lots of circles in the Euclidean sense, which are perpendicular to the black circle passing through the point P. And those are all hyperbolic lines. And all those hyperbolic lines they don't meet the line L. So they are all parallel to the line L. And there's like infinitely many. And so on. So because of the way shortest paths end up looking like, the way you measure distances, Euclid's fifth postulate fails badly. So here it's like in spherical geometry, it was failing for stupid reasons, but here it's like genuinely failing. I can find infinitely many lines to the point P that are parallel to L. Any questions so far? Okay. Okay, so that's all abstract. Like I described you the hyperbolic two space, and I like showed you basically different models of hyperbolic two space. Now, where does hyperbolicity show in real life? So when I say hyperbolicity, it's like basically this notion of negative curvature. Did I say curvature? Yeah, I guess since these triangles are thin, somehow we think of this as negative curvature. So if you have Pringles or chips or Uncle Chips, they have this saddle shape. And so here I've like shown a saddle. So in a saddle, if you draw a triangle, that looks like a thin triangle. And in basically in hyperbolic plane, every point is a saddle point. Like on a piece of chips, you'll have one point which is a saddle point. But imagine in hyperbolic space, every point is a saddle point. So at every point you are like curving weirdly, which is why it becomes hard to put hyperbolic two space, hyperbolic plane in Euclidean three space. Because at every point you need to be like seeing the saddle in some sense. I guess there's someone at Cornell, I think they crochet these, all the, I guess coral reefs. Coral reefs have a lot of structure which resembles hyperbolic geometry. So they have a lot of negative curvature. They're like negatively curved. And this is just a picture. This is just a picture of someone drawing corals using crochet. And I guess they were even in this picture, they are even like drawing. It's like this is a line. Here is a point, and they've drawn all these like different lines parallel to the line, which are not meeting that line. So the fifth postulate is failing. So they tried drawing it in this crochet model of coral reefs, of corals, not reefs. Some of you might have seen this picture, Escher's circle limit 3. So Escher is he's a famous, I guess, artist / mathematician. So he has like these beautiful drawings, which were inspired by hyperbolic geometry. So there's like, you can see there's some hyperbolic geometry. He's trying to draw the Poincaré model. Okay, so I guess these are cute examples for hyperbolic geometry. But here is like this is a big result. So if you look at, so I have to add some adjectives, and it's okay if you don't quite know what these adjectives mean. Every simply connected Riemann surface. So basically every two-dimensional surface, and of course I have to add adjectives to it because I can draw crazy two-dimensional surfaces, but every nice looking two-dimensional surface can be given one of the three geometries. It's either Euclidean, either spherical, or hyperbolic. There's nothing else. So if you give me a nice enough surface, these are the only three options that space has to be. So that's pretty big. It's not like there is something crazy, there's something else crazy going on a surface. This is all that can happen. And we understand all three pretty well now. So when someone asks me what's an application, I would say this is a big result to understand what two-dimensional surfaces only three options very well at this point. In Euclidean space is flat. So this is like curvature 0, curvature -1, curvature +1.
Ma'am, what about torus?
That's a good question. For torus, usually we draw it like this, and we think it's like curved. So that's an embedding of the torus. But usually, so basically, if you take a square, if you fold it into a cylinder first, if I can draw this. So I fold it into a cylinder, and then I fold these two sides to get this picture. So because I start with a square, for me, a torus would be a Euclidean geometry. Because I've just started with a square piece of paper and I've identified two sides. But everywhere, if I want to measure angles and distances, it's all Euclidean geometry. Yeah. So then maybe because you asked this question, I can say there is a classification of closed oriented surfaces. So these assumptions are very important. It's either a sphere or a torus, or basically taking two torus and like gluing them together, or three of them, and so on, or 4 or 5 and so on. I should say this is more of a topological result. So this is topology, and in this talk we have been talking about geometry. So like the sphere will have spherical geometry. The torus, like I explained here, will have Euclidean geometry. Okay, so just going back to this theorem. If I give you a nice two-dimensional surface, it has only 3 geometries that are spherical, hyperbolic. That's pretty impressive. There's not much else. So that's for 2 dimensions. And for 3 dimensions, there is this big result called geometrization conjecture, and now it's called a theorem. So if I give you a three-dimensional topological space, and I guess there are lots of adjectives which I decided to not write. Not lots, but some adjectives. Every three-dimensional space can be decomposed into pieces such that each piece has only one of the following 8 options. Okay, so maybe it's possible to glue the pieces in funky ways to get something weird, but each piece, so there's a well-defined notion of what a piece is. Each piece has only only one of these 8 things. So we have a finite list for each of these pieces. And some of these I think we understand, but some we don't. We as in like me, but like mathematicians in general understand these spaces. So Euclidean space, spherical, hyperbolic, that's similar to the 2-dimension case. But then there's the geometry of like sphere cross R, geometry of hyperbolic 2 space cross R. Then there's a group of matrices, 2 by 2 matrices of determinant 1 that has some geometry. There's another group called Heisenberg group that has some geometry, and then some I guess the last ones are, I'm not very familiar with the last few cases. But the point is that there are these like 8 options. After you can, for each well-defined piece of your 3-dimensional space. So this was a conjecture of William Thurston in 1982, and then it was proved by Gregory Perelman in 2003. And actually, like this is a very like geometry topology kind of conjecture, but the proof was using something called Ricci flow. So like a lot of partial differential equations, analysis, like lots of different areas of math were being used to prove this thing. So I guess for 2 dimensions, we know there are only 3 options. For 3 dimensions, we know there are these 8 options. So then the question is, what is the geometry of the universe? So we don't have an answer, but we know that if you could break it up into like small pieces, these are the only options we have. So that's already like a lot of progress in our understanding in some sense. But we don't know what the universe looks like because we might have to like zoom out a lot. Just like sitting here, already we thought the earth was flat like many years ago. We had to zoom out or like do some analysis to say that it's actually a sphere. So the universe, I don't know how much we'll have to zoom out to say that it's actually not Euclidean or not hyperbolic. So we don't know. I think I'll stop here. Thank you.
Thank you, madam. Any question from the audience? Any question?
Yes. Ma'am, it was a wonderful presentation and very colorful and very much attractive presentation. First off, I would like to congratulate you.
Thank you.
My question is not related to this your talk, but a general question. Ki your belief, does there exist life? अर्थ के अलावा भी कहीं लाइफ हो सकती है? I want your personal view. I want your personal view.
Maybe. I don't know. I guess I think about too many abstract things, and I mean, there is no reason to not believe that, but I also don't have any reason to believe that strongly. I don't know.
Okay, मतलब ये ज्योमेट्री तो 8 में से कोई एक होगी.
As long as we can break our universe into small enough pieces, like nice enough pieces. So the theorem is very strong. I'm not saying that every 3-dimensional space can have only one of these 3 properties. I'm saying every space can be broken up into pieces. Then there is a well-defined notion of what a piece is, such that each piece will have only one of these.
Okay, yeah. One more quotation I would like to share with you.
Mm-hmm.
In some geometry, 2 parallel lines meet at infinity, right?
Mm-hmm.
Once geometry, I think which one is 2 parallel lines meet at infinity? In some geometry, maybe projective geometry, or I don't know exactly. But so there is a quotation. If any 2 parallel lines meet at infinity, then infinity must be a noisy place. Thank you.
Okay.
Thank you.
Thank you. Thank you, Thakur sir. Any question other than Thakur sir? Okay, thank you. So very nice lecture, and she has explained 3 geometry: Euclidean geometry, spherical geometry, and hyperbolic geometry. So the main focus is fifth postulate of Euclid, where it is failed, in which geometry it is failed, and she explained very nicely this postulate is failed in hyperbolic geometry. She explained some hyperbolic model such as Minkowski space Poincare models for hyperbolic plane, and some. Lastly, the question is what is the geometry of the universe? And the question,
Sir,
answer.
can I ask question to ma'am?
Okay, you can.
Ma'am, so we have a question that what is geometry of unions?
Mhm.
I think there is an geometry that connected geometry where begins, start and ends are connected together. As our Purans or Ved says, Ant hi Aram or Aram hi Ant hai. uh, that's way our universe geometry can be possible.
Aditya, that is what Madam started with. What is the geometry of the universe? And ended with what is the geometry of universe?
You don't know. So,
Okay.
thank you very much, Madam Radhika. Madam.
Thank you so much.
Thank you. Thank you.
Thank you, Radhika ji, for
Thank you.
for having a tour to Gujarat, at least virtually, and hope to see you. Hope to see you because, to my knowledge, you are joining TIFR very soon. Am I
Yes.
right?
Yes.
Yeah. So
Last
we'll meet
comment.
personally in Gujarat.
Okay.
Yeah.
Yes.
Last comment, ma'am.
Thank you.
राधिका मैम,
Yes, sir.
Yes, sir.
आपके जो हैंड राइटिंग है
हाँ.
उनकी कर्वेचर पॉजिटिव है, बहुत अच्छी हैंड राइटिंग है.
Thank you.
Yes, ma'am.
So thank you, madam, for accepting invitation.
Yeah, thank
and
you for
having,
inviting me.
Yeah.
Yes.
Yes, sir.
ma'am,
Srimani,
I
sir.
just want to say,
Karan, what?
ma'am, this is Karan here.
Yes.
Hi.
What is
Very
your
much interesting stuff.
Yes.
So thank you.
Okay.
Thank you so much.
Okay. Thank you. Thank you, ma'am.
Thank you.
Thank you.
Bye.
So we conclude the session and goodbye, madam.
Bye.
Recording
Bye-bye.
stopped.